Hi, class. This is the first lecture in topic 12, which we're doing as Unit 10, but it's the HL form of Unit 10. So we're in the topic 12, quantum, nuclear, and particle physics. We're going to look up real quantum analysis of particle motion. So in this lecture, we're going to do this first objective, in which we are going to describe and calculate the behavior of particles through the understanding of wave-particle duality. We've already seen wave-particle duality occur with light waves, and now we're going to look at how particles can also have wave-particle duality, which is going to be really weird. We're going to discuss experimental evidence for this, and we're going to call them matter waves. We're going to include an experiment, which the wave nature of the electron is evident. We're going to describe a scattering experiment involving the location of minimum intensity for diffracted particles based on a new wavelength, which we're calling the de Broglie wavelength. The good news about this is a lot of what we're doing in this lecture is an application of previous knowledge. The only thing that's very weird, and was weird when this idea first, was accepted, was brought up, is that we're just applying it in very, very strange, weird quantum ways, such as like the fact that there are matter waves. So this idea that came out early in 1900s was from de Broglie, and he stated that if light have wave-like and particle-like properties, such as in an electromagnetic wave, and photons, then why don't particles also have wave-like properties as well? And that is the de Broglie wavelength-like statement. And though many scientists were like, silly de Broglie, that seems just way too weird. They found out through experimentation that electrons also produced interference patterns similar to light. So in this experiment, we have an evacuated tube that's just there due to the nature of electrons. We didn't want any outside forces or anything at play. You shot off electrons using this electron gun. It gets sent through some sort of voltage to have it gain some speed and gain energy, kinetic energy. And it passes through a thin graphite screen, which acts similar to a diffraction grating. And they found that depending on how much voltage they applied to the electron, so how much speed the electrons gained, they noticed different interference patterns. So these are interference patterns of electrons. They found that there is differences in the distance between maximums and minimums depending on the speed of the electrons. And we're going to get to that later, but this is actually not the original experiment that produced it. This is just a very easily observed way of showing this. In order to look at the experiment, we're going to look at something that occurs with light first and then show how that compares, because we're actually looking at a different type of interference we haven't really done, at least mathematically, about. And that is like it's reflection interference. It is observed specifically with CDs. And this is due to there's ridges on the CDs, and the different distances of the ridges, of like the gaps, produce this interference pattern. And we also see light. It's very similar to thin film interference, except there's just no index of refraction. It still produces these rainbow colors. So this occurs due to constructive and destructive interference, which is why we see different colors, red, green, yellow, on these CDs. But what they did is they said, you know what? Let's take electrons and shoot them at some sort of grating, kind of like that, kind of this reflection grating, and see what happens. So let's watch this, and then let's explain it.
Experiment, which is now known as the Davison-Germer experiment, involved bombarding the surfaces of different oxidized metals with electrons. It was observed that if the surface of the bombarded metal was not oxidized, the voltage distribution of the reflected electrons formed maxima and minima, depending on the observation angle and the kinetic energy of the electron, in the same way as if the electrons were waves and underwent diffraction and interference. When in 1926 Germer heard about the concept of de Broglie waves, he realized how important his own discovery was and immediately published his results.
So in this experiment, nickel was heated up to remove any oxidation. That helped form a crystallized surface that pretty much acts similar to a CD's surface. Low energy electrons were then shot at this nickel and then were scattered off. In other words, for scattering is reflecting. Those scattered electrons diffracted and created this interference pattern that the observer, the detector, was able to measure. That interference pattern was very similar to the way that electromagnetic waves interfere through a diffraction grating. After doing some analysis at different speeds, different energies, they found a pattern and were able to come up with a wavelength for an electron that matched de Broglie's originally proposal. And why do we need to use this electron? How is it useful? Well, it has to do with the orders of magnitude of the wavelengths. We've already talked about how in order for diffraction to occur well and for us to be able to resolve different images, the smaller the wavelength, the better we are at resolving smaller objects. So visible light has a wavelength that's in the order of magnitude 10 to the negative 7th meters, X-rays 10 to the negative 10th, and electrons undergoing a potential difference of 100 kilo electron volts is 10 to the negative 12th meters. So we might use something like an electron microscope like this to help resolve the distance between two objects. So let's go back to resolvence and how we're using kind of a form of Rayleigh's criterion, but trust me, it's super simplified, and I typed microscope wrong. Well, oh well. So when we look at the resolution ability of our eyeball with visible light, it's only 0.2 millimeters. A visible light microscope, one of the best, gets down to 0.2 micrometers, which is 200 nanometers, and then an electron microscope is about even slightly less, but it's around 1 nanometer. So we're able to see nanoparticles with electron microscopes. So that means we're going to get images that look like this. We're going to be able to see, the resolution of a fly. We're going to be able to, the second one is the eyeball of a fruit fly. And the last one is a tardigrade, which is the smallest living object and the most resilient living thing on Earth and maybe elsewhere. So this is why we're going to use it. Now, that means that we must look at the equations that are involved in diffraction. So we're going to go back to what we've seen before, these same equations we use with electromagnetic light. So our diagram for the Davison-Germer experiment shows this. We might see a beam intensity and that has certain maximums and minimums. We're going to focus on the minimum. You can think when we look at the distance between objects, we are looking at it as a single slit, as that's the distance between the objects, or the size of an object, depending on what we're looking at. And we're going to use this equation where theta is the theta with minimum intensity. The lambda is our de Broglie wavelength. And our d is the size of object. Whatever we are measuring, it's the size of that object. So we've kind of looked through a very conceptual understanding of matter waves and why we use it, and we're starting to get into the equations, but we haven't yet actually identified the de Broglie wavelength. So let's do that. We have learned in the past that the energy of a photon is equal to Planck's constant times the frequency, which is also equal to hc over lambda. And we haven't seen this equation before, but this is just the energy of any object, and technically it's the rest mass energy. But in our level of physics understanding, this is just going to be the energy of anything. All right, so E equals the mass times the square of the speed of light. Now, we have to do some, of course, approximating, but this is exactly what de Broglie did, so we're okay with this. I'm going to plug in hc over lambda on the left side, and then I'm going to write this as m c squared. Now, technically, c is the speed of light, so I'm going to actually write this as hv over lambda because we're looking at the speed of an electron equals mv squared. So, of course, you're already noticing, whoa, that's weird. We have some approximations going, but just roll with it. So, our v squared cancels just a v on the right side, the v cancels on the left, and then I'm going to divide by mv. So I'll have, and multiply by lambda. So I get h over mv is equal to wavelength. And look at that. We have, this is the equation for the wavelength of an electron. So this is h, let's write it as lambda, is equal to h over mv. That's our momentum. And this is our de Broglie wavelength. Seems strangely simple. Though strangely simple, it is used in any calculation in the technology for these electron microscope images, so it actually matches fairly accurately to what we want. There's one more trick that you can use when trying to determine the de Broglie wavelength, because you need to find momentum. In order to find momentum, you need to find velocity. In order to find velocity, you need to find how much energy it was given, how much kinetic energy it was given. So this equation, also, one thing, is these equations are not in your data booklet. So you'll have to memorize this. You'll have to. And this next one is going to not be in your data booklet either. So when an electron is accelerated, it is accelerated through passing through a potential voltage, right? Electric potential. So we can say that we have a change in EK, which is equal to some change in EP. In our data booklet, we have this equation, EK is equal to P squared over 2M. So I'm going to plug that into my left side, and my energy gain from passing through a voltage is going to be E, which is the charge of the electron, times change in voltage. And I want to solve for P. So I'm going to multiply 2m over. I get P squared is equal to 2me, and then I'm just going to write V, knowing that that's the voltage that it's accelerated through. And we find P is equal to square root of 2m EV. This will actually become helpful for you to just know you can solve fairly fast in these de Broglie wavelength equations, because then I can also say that lambda is equal to h over P, which is square root of 2MeV. Because generally when we deal with electrons in electron microscope and electron diffraction, we are going to be passing the electron through some voltage for it to accelerate, to have some momentum, to have this de Broglie wavelength, for it to be able to diffract. So it might be useful to memorize this, or just to know how to derive it quickly. So that's the equations for all the concepts that we just learned. Let's apply them. So now what's silly is that we've been talking about electrons, which are like, atomic particles, but every piece of matter has a wavelength attached to it. So let's determine my wavelength. Let's say I'm in a car and I'm driving at 20 meters per second and I'm 70 kilograms. So let's see what my wavelength is. So first, I want to identify my momentum. That's 70 times 20. Right, so it's 1400. And I already know what my Planck's constant is. That is in our data booklet. Let's find that. Ta-da, there it is. So 6.63 times 10 to the negative 34th joules seconds. So let's find my wavelength. It is 6.63 times 10 to the negative 34th joule seconds. Divide by 1400, that's kilogram meters per second. And I get 4.74 times 10 to the negative 37th meters. Now that measurement is very, 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 very small. We have a very small wavelength. I do. And every one of us does. Very, very small. Now, we don't have the language or the knowledge to explain what that actually means at a quantum level, but it does have to do with when we get to the wave function and probabilities, as why we aren't able to quantum tunnel and walk through walls. But again, we don't have the language, so let's wait for that. And we just know that we have very, very small wavelengths as our whole mass of body, 70 kilograms. Okay, number 2 is an electron is accelerated from rest through a potential difference of 215 volts. What is its expected de Broglie wavelength? Now, going back up, I just gave you this equation where we can just plug and chug, but I'm scared that you might not memorize this equation if, on the assessment, and especially on the IB exam. So I'm going to go the long route because that's the route that most likely you will probably take on the IB exam if you don't memorize that equation. So I have a voltage, 215 volts. I also know my charge of an electron is equal to 1.6 times 10 to the negative 19 coulombs. I have a change in potential, which is 215 volts. And I know that E delta V gives me a change in kinetic energy, which is 1/2 mv squared. So I have 1.6 times 10 to the negative 19th times 215 is equal to 1/2 the mass of the electron. Well, mass of the electron, this is in your data booklet, is 9.11 times 10 to the negative 31st. So it's 9.11 times 10 to the negative 31st times v squared. So doing some algebra, we'll end up with some v is equal to something. So the velocity came out to 8.69 times 10 to the 6th meters per second. Don't forget to square root it if you end up with if you ended up with times 10 to the 13th power. All right, so we have the velocity, which means we can find our momentum, and I know my wavelength is equal to h over mass times velocity. So my h is, as seen above, 6.63 times 10 to the negative 34th, divided by my mass, which is 9.11 times 10 to the negative 31st, times my speed, which is 8.69 times 10 to the 6th. So after plugging these values in, we'll end up with a wavelength. I got 8.37 times 10 to the negative 11th meters. That's our expected de Broglie wavelength. All right, and number 3, we have a beam of 75 mega electron volt neutrons. Oh, we have neutrons. They're diffracted upon passing through a thin metal foil. The first minimum in the diffraction pattern is measured at 2.5 degrees. Estimate the diameter of the metal's nucleus. So we know we have to use sine of theta is equal to lambda over d. And we also know we're going to have to find the de Broglie wavelength of a neutron, which we're going to go h over p. But we know that that momentum is of a neutron. So we'll need to know the mass of a neutron. This is in your data booklet. It's called rest mass, and every single thing we measure is going to be in rest mass. It just makes our situations simpler. This is 1.675 times 10 to the negative 27th kilograms. What else do we have? We have the energy of the neutrons is 75. Oh, it's in mega electron volts. That's going to be kind of annoying. And we have the theta min is equal to 2.5 degrees. I might actually move this over here because I know it's a variable I'll need when I get to that equation. And we need to find the diameter. So I'm pretty sure in these situations and in all IB problems, the world's going to be quite simple in these topics. And that means that D is the diameter. That's what we want to find in that equation. They'll never overcomplicate and make you have to think through it because a lot of this is approximations anyway. So they just want you to follow the process of thinking through this, follow the process of the math and so forth. So I think the hardest part here is identifying how to get the correct momentum for the neutron because we have mega electron volts. So if you want to pause and try to play around and get to it, please do so. But I'm gonna work through it myself. All right, so the first thing I'm going to do is I'm going to convert electron volts to joules. I know that 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. That's just by definition what an electron volt is. And by converting, I get 1.2 times 10 to the negative 11th joules. Now, I'm going to give you a hint at a trick that I'm going to use. I'm going to use my kinetic energy is equal to P squared over 2m. So I can go directly to P, so I can skip over the 1/2 mv squared, and I don't have to deal with mv. I can just use P. So I'm going to pause this so we can work on this. So after plugging in my kinetic energy to solve for P, I end up with a momentum of 2 times 10 to the negative 19th kilogram meters per second. Using de Broglie wavelengths equation, lambda is equal to h over p, I get a wavelength of 3.31 times 10 to the negative 15th meters. And that's the wavelength that I'll need to use in this sine of theta is equal to lambda over d, where we're solving for d. So plugging it in, I get my size of my object, which is in this case the diameter of the atom, to be 7.58 times 10 to the negative 14th meters, which is fairly close, because we know that atoms have a radius in the order of magnitude of times 10 to the negative 15 meters. And we're done. So I hope this helps, and I will see you in class.